right, hello everyone. You look very enthusiastic as usual. And it's great to see the whole class here. Okay, so let's talk a little more about our famous second-order system. The one we parameterize with the damping ratio zeta and the natural frequency omega n. So we talked about the frequency response of this in the previous lectures. The last lecture was about Bode plots, where we make a simplifying assumption that zeta is 1. Therefore, you have 2 repeated poles, even if that's not the case. And we discussed why that will not be very accurate if zeta is actually much smaller than 1, because then you'll be missing out on these resonance peaks. That might be an important feature of your frequency response. And then there's the impulse response and step response that we didn't talk much about. So I'm going to talk about these today at first, and then we'll move on to other things. All right, so second order system, H of S has this form, remember, omega n squared, S squared plus 2 zeta, omega n, S plus omega n squared. We write it in this form with omega n squared in the numerator so that the DC gain is equal to 1. Remember, DC gain means frequency equal to 0, therefore S equal to 0, and you get 1. Just normalize. If it's not, it's not. Then you just factor out that constant. Okay? So zeta, as we know, is called the damping ratio. And omega n is called the natural frequency. And the poles of this system are at these 2 points. They are complex conjugates. So in this representation, we implicitly assume that C is between 0 and 1. If zeta, not C, zeta. If zeta is in this range, then we're going to have complex conjugate poles. In fact, when zeta becomes 1, they collapse into repeated real poles, right? So we consider zeta in this range because if we go above that, then you have 2 distinct real poles. And why should we bother writing it in this form, right? I would just write it as 1 pole times another pole, right? So that's why we assume zeta is in this range. Okay, so the poles then are at these 2 values, minus omega n cosine theta. We defined theta last time, and I'll tell you again. J omega n sine theta. So what is theta? Theta is a number such that, an angle such that cosine theta is equal to zeta. All right, so essentially what we are looking at is poles. So this is real axis, this is imaginary axis. Poles are on this half circle. That wasn't a very good one. Okay, so pretend this is a half circle, although it looks more like an egg shape, okay? And the distance is omega n, okay? So the radius is omega n. And then the poles are complex conjugate, and they are located here. So theta in this picture is this angle. All right? So clearly, if you look at the actual pole locations, the ratio of the imaginary part to the real part is sine of theta by cosine of theta. So that's tangent of theta, right? So in this representation, cosine of theta is the is C. All right. So what we're going to do is we're going to call this omega and cosine theta sigma, because that really is the real part of our poles. Okay. So sigma is this point. So this point here is negative sigma. Okay. That's the real part. Imaginary part is this, and we're going to call it omega d to distinguish it from omega n. because omega n is actually here. So the two are not the same, right? They'll be the same only when zeta is equal to 0, because in that case, the poles will hit the imaginary axis. Okay? Makes sense? So this is an important picture showing us where the poles are and how that depends on zeta. And the precise relationship is through this. Okay? All right. So then the question is, we can ask several questions here. The first question is, what is the impulse response of this system? Because that's one of the 3 plus that I showed you. Frequency response we already discussed. Next up is impulse response. So let me give you some hints, but I'll ask you to do it, okay? So the question I'm asking is, what is the impulse response? So if I give you h of s, how do you get the impulse response? You take the inverse Laplace transform. Now, there's no reason to, you can do partial fraction expansion and all that to do this, which is fine by me, but we can actually be a little more practical than that. So what I'm going to do is I'm going to write this in this form. So now that we found the real and imaginary parts, I can actually put the denominator in this form. Do you agree with this? So when I look at the poles of the roots of the denominator, right? That means the denominator must be equal to 0, right? And that means s plus sigma is plus minus j times omega d, right? Anything like, z squared plus omega d squared equal to 0 implies z is plus minus j omega d, correct? Agree? Now, substitute in place of z s plus sigma, right? And now you get these poles that I was talking about, right? So that's how I was able to write it in this form, okay? I don't see many of you objecting, so I'm going to erase this. All right, so if you believe this, then you should be able to take the inverse Laplace transform, not necessarily take the inverse Laplace transform, just infer the inverse Laplace transform from the Laplace transform pairs we've seen and the properties we've seen. So hint, one property we saw was that if I have a signal x of t whose Laplace is x of s, if I multiply the same signal with e to the s0 t, the Laplace transform will be what? No convolution. This is a property we saw, right? What do I do to x of s? Shift it. X of s minus s0, okay? So we saw that. That was last week, or maybe even before. The second thing we saw in that same lecture, whenever that was that if you are interested in the Laplace transform of a sine, then it is, okay, let's see how well you remember, if you remember at all. S squared plus omega naught squared. Now what goes in the numerator depends on whether it's sine or cosine. When it's sine, you put omega 0. When it's cosine, you put s. You were close, but you mixed it up. That's okay. You have 2 more weeks to get that right. All right. So using these, can you tell me, and I'll give you a minute to think about it, can you tell me what h of t is? I'm giving you those hints so you don't actually have to do partial fraction expansion and all that stuff to find the answer. Just piggyback on what we already know. Okay, I wrote one more thing that might be helpful. And I'll carry over this here. This is just a factor. Omega d. Now you have no excuse not to tell me what the inverse Laplace transform of this is. Good thing we postponed the midterm. Just kidding. I'm sure you already see this. So someone, speak up. Use your courage. Give us the answer. What's the worst case? If you're wrong, I'll just publicly humiliate you. What's wrong with that? Yes? Yeah, yeah. Uh-huh. Sine omega d y squared, omega dt, right? U of t, right? You all see this? So that multiplication with e to the negative sigma t, all that does is just first pretend it's not there, then the Laplace transform of what remains is basically like that, right, with omega 0 replaced by omega d, right? And what this does, according to this, is make s into s plus sigma. So there's only one s here, and it's this s. So if you replace this s with s plus sigma, you get this expression here, right? And this factor here was accounted for here. So this is h of t. Okay, I did this as a warm-up, also as a quite refresher for some of the properties of Laplace transforms. So let's go back and look at this. So this is basically what you're seeing here. The time axis is actually not just time divided by omega n. And these are the impulse responses you're seeing. The smaller the zeta is, this is the legend up here at the top. Like the blue one is the smallest zeta. It's 0.1. When zeta gets smaller, you see that this h of t, even after division by omega n, is giving you bigger peaks. So first of all, you should be able to see the sinusoidal thing in there, multiplied by e to the negative sigma t. That's why it's a decaying sinusoidal, right? That's consistent with what we just derived. And then this factor that I put in orange was omega n squared by omega d. This is plotting that by omega n, so really there's a factor of omega n by omega d multiplying sine. So when zeta is smaller, that factor grows bigger. All right, that's why for the blue curve, which is for zeta equal 0.1, you're getting a bigger value, bigger amplitude. All right, so that was a warm-up, but I really want to talk today about the step response. That's arguably a little more important than the impulse response. Why? For example, next week we'll talk about some examples of how we design feedback controllers, right? There, one of the goals is to make the system follow the commands. Like a pilot might command a certain altitude, and you want the system, the aircraft in that case, to reach that altitude, right? How do I reach that altitude? Do I overshoot, come back down, go up? Or do I go smoothly? How fast do I go up? All of those are problems of step response, right? Step being the reference command. I'm telling you to go up, so many feet up, right? And then the response is what you're actually getting. So understanding the step response from a transfer function is critical, and doing that for a second-order transfer function is the first step. And in fact, a lot of times for higher-order transfer functions, people use second-order transfer functions as a simplification. I'll talk about that later. Okay, so let's think about the step response of, again, our transfer function h of s omega n squared, s squared plus 2 zeta omega n s plus omega n squared, right? How do I find the step response? Step response means x of t is u of t, and then it goes to our system, h, and the output is y of t, step response, right? So how do I find it? Now that we know about Laplace transforms. The way not to do this is to use the impulse response, take convolution with u of t. That would be a mess. Why would you do that, right? So what's an easier way? So think about the Laplace transforms of everything, right? So y of s is the transfer function h of s times x of s, right? This is a very important thing about LTI systems and Laplace transforms, right? Convolution becomes multiplication. So we can use that because I know the Laplace transform of the unit step. I know the transfer function. I can multiply them. And I find y of s. How do I go back to y of t? Do an inverse Laplace. Okay? So what is the Laplace transform of the unit step? 1 over s. So overall we have omega n squared. The only difference from h of s is I'll add another s in the denominator to account for 1 over s from the unit step. And then the next problem will be how to do the inverse Laplace transform of that. A good way of doing that is always the partial fraction expansion. We actually did something like this without this s in the denominator just a minute ago, right? And in that example, we just compared it to the Laplace transform of a sine function, and that's how we did it. But now we have another s. So let's do it the more proper way, or the partial fraction expansion way. So first thing to note, though, is that what we are seeing here, remember that had two poles, right? Negative sigma plus minus j omega d. So I can really factor this in this form. S plus sigma plus j omega d. S plus sigma minus j omega d. You all agree with this? If you multiply this out, you're going to get s plus sigma squared plus omega d squared, which is exactly what we discussed here, right? So that's why we wrote it this way. Right? So then I have three poles. Two of them happen to be complex conjugates, and one of them is at 0, right? For y of s. So what I'm going to do now is propose a partial fraction expansion. A over s plus b over s plus sigma j omega d, okay? And then another number for the other pole. But now look at these two poles. They are complex conjugates, right? For a transfer function, when you're doing this partial fraction for complex conjugate poles, the coefficients have to be complex conjugates of each other as well, all right? I'm writing this without proof as a fact, but the premise of this, the reason why I'm claiming this is because if they didn't match up, if B and the other one were not complex conjugates, then when you simplify this, you're going to end up with complex coefficients. So if you're actually decomposing a transfer function with real coefficients, then complex poles you can write this way, but the conjugates will have the same coefficient conjugate. All right? Does that sound reasonable? Okay, that will save some time. So, all right, then we have to, do the simplification, etc. So, and I'm going to cut corners here a little bit, so I'm not going to write down everything. So when you match coefficients, and I assume we can all do that, you'll find A to be 1, B to be, and don't expect a real number here because it's representing a complex pole, negative 1/2, 1 plus j times sigma by omega d. Sigma, remember, is the real part, and omega d is the imaginary part. Okay, so it's complex. And B star is, of course, the same thing. You just replace J with negative J, because it's the complex conjugate. All right? So can you tell me what y of t is then? Everything I write is going to have a factor of u of t. All right? So let's take care of that once and for all. So A over S, and A is 1, so it's 1 over S. What is that going to give you? Unit step, right? That's it. So I put a 1 here. All right, B over S plus sigma j omega d. It's going to give us B. I'm going to leave it as B for now. Times e to the what? Minus sigma t and negative j omega d t, right? And now for B star, same thing, except I'll have e to the j omega d t without the minus sign. Okay, so some simplifications are clearly hiding here. I can write, first of all, I can factor out e to the negative sigma t because it's common to both. And then I have b e to the negative j omega d t plus b star e to the j omega d t. Now, there are two terms here, this and that. And do you agree they are complex conjugates of each other? If I multiply two complex numbers and take the complex conjugate, it's the same as multiplying the complex conjugates, right? So that's why one is the complex conjugate of the other. So therefore, I have b e to the negative j omega dt plus its conjugate. A complex number plus its conjugate is equal to what? 2 times the real part, right? So this expression in orange then is 2 e to the negative sigma t, the real part of b e to the negative j omega d t. Now, b is a complex number. It has real part here, imaginary part here. This also is a complex number. It has real part cosine omega dt and imaginary part sine omega dt, right? So I trust that you can actually multiply two complex numbers and find the real part of the product. So I'm not going to do that. So I'm just going to give you the result instead. And that is in here. Here. Okay? So everything I did is all done in detail here. So the final expression for y of t has this form. Any questions, guys? Step response, well, why did we look for the impulse response? I mean, it's part of the second order system. I said that the step response is a little more important because when we design feedback systems, one of the things you want to be able to do with the feedback is to make sure you can follow step inputs, because those will be commands. When you're driving, and if you set your cruise controller to a certain value, let's say you are going with 65 because the police car is there, and then you're out of sight, you push 75 now, right? I'm not suggesting you do that, but just for example. So it's a step of 10, right? How is your car going to handle that? There's obviously a control system in there that makes that command happen, right? So the system with the controller, we discussed how to derive transfer functions from the reference to the output last time, and we'll revisit that soon again. So let's imagine that's a second order system, right? Then you want to be able to shape that frequency response, and there are some trade-offs there. If you want to go to 75 really fast, right, you may have to handle overshoots and things like that. If you don't want those, you may be going too slowly. So what are the right trade-offs? So that's why understanding the step response is a fairly important thing, more so than the impulse response. Okay, so anyhow, this is the step response. Okay, so it shows you everything you need in there. Clearly, the second term there, the one that's multiplied by e to the negative sigma t, that's going to disappear over time, right? And therefore, in the limit, as t goes to infinity, this will settle at 1. Which kind of makes sense because we apply the unit step whose steady state value is 1. And the DC gain of the system was 1, right? So it should the output also should settle at 1, right? So essentially, this is an oversimplification, but 1 is always there, right? So I'm going to try to make a little plot. So 1 is here, and then there is sort of a funnel on top of that that represents this envelope with e to the negative sigma t. And inside there, you see some oscillations hidden, right? So that's why you're going to see a step response that looks sort of like this, okay? And it will settle at 1, right? So that's a very rough sketch of what that y of t, what shape we should expect, yes? Real part of which complex? Oh, that's because, so that's what I just said. So this, you're adding this and this, right? But one is the complex conjugate of the other. So if I add a complex number to its conjugate, what comes out is the real part multiplied by 2. That's why we're taking the real part. We're not ignoring anything. It just happens to be equal. It's not an approximation. Okay? So let's go back to the real step response shown here. This is showing the step response for several different values of zeta. Okay? And that is consistent with what we have just derived. You can see that you're going to have oscillations before you settle if your zeta is small. Zeta is called the damping ratio. So small zeta means small damping, really. And that's why, you know, a poorly damped system will have oscillations before it settles down. A well-damped system where zeta is high, close to 1, will not oscillate. It will converge uniformly. I mean, it will converge monotonically. So you're kind of seeing that here, right? So, okay. So the step response has several important features that one cares about when perhaps designing controllers, right? So one question is, you know, what is the rise time? What is rise time? Rise time means there are various definitions, but essentially, how far do I get to 1? And how do I even measure that? Because I only asymptotically go to 1. One definition that's practically used is the time to go from 10% to 9% of the final value. That is, if the final value is 1, as in this case, well, how much time does it take between the time that the step response was 0.1 to the time that is 0.9? Okay, so the assumption here is by the time you get to 0.9, you're pretty close to the final value, so that's how long it takes to rise. Okay, so that's one important feature. The other important feature, so I'm telling you about these features because when you're designing, say, a controller, you might have in mind a certain rise time that's appropriate for the application, or a tolerable amount of overshoot that's appropriate for the application, and then you may want to translate those to an appropriate zeta and omega n. Okay, so what we are going to do in the next couple of pages is relate these properties, the rise time, the overshoot, peaking time, settling time, etc., to zeta and omega n. That way, if you have requirements for your design that says, I want a rise time that's 1 second, and I don't want to overshoot more than 5%, those types of things can then be translated to the coefficients zeta and omega n. Okay, so that's the goal of this. So rise time is as explained. Peak overshoot means, you know, you're trying to go to 1, but you may have to have a big jump along the way if your damping is not good enough. How much above 1 did you go? That's what peak overshoot means. So in our running example, the steady state value is 1. But in general, it can be 10 miles per hour or something like that, right? So therefore, in defining it, what we do is we look at how much overshoot we did, peak value minus the actual steady state, and scale it by the steady state. And that gives you a percentage overshoot, right? So clearly in the blue curve, you're seeing a peak that's more than 1.5. So you're looking at overshoots more than 50%, right? Would you be happy flying on an airplane that has an overshoot like that? Especially in landing, you probably don't want undershoots, right? So again, these things very much depend on the application, what is tolerable and what's not. Peak time is the time at which we reach the peak. In this picture, that would be this time. The peak happens here for this particular zeta, the blue curve, and the peak time is here. All right? Settling time. Settling time is when do all these transients, the oscillations and all that, die down and I'm really close to 1. I can't say when exactly I'm equal to 1 because the answer is infinity. I only asymptotically converge to 1, right? But I can ask, when am I within 1% of the final value, 1 in this case, and I never leave that again, right? So, of course, you can't say when is the first time you're within 1% because that will be around here. You want to know the time way out here when you are really within plus minus 1% of the final value. And you never leave it once you're in there. Okay, you're interested in that point. So that's called the settling time. By that time, for all intents and purposes, you're at your destination and you're not going to go far from it. Okay? So how do we derive these things? Or relate those features to omega n and zeta? They are really easy once we have this expression for y of t. Okay? So how do I, for example, find the peak time when we reach a peak, which is this point, right? What is a good way to determine when we reach the peak? By looking at y of t. What happens to the curve at the peak? What's its slope like? 0. So one way to do this would be to set the derivative equal to 0 and see what t is solving that, right? So if I look at this expression, look at y prime for t positive, so I don't have to worry about this unit step. There will be several terms, but there will be cancellations as well. The first, you look at the derivative of cosine omega dt, and that's negative omega d sine omega dt. Am I doing that right? I still remember my trigonometry. Okay. Wait, actually. Yeah, okay. So let's first take the derivative of what's inside. Okay. And then sine will give me cosine, right? And then omega d's will cancel, so I'll get sigma cosine omega dt times e to the negative sigma t, right? Now, we have a product of two terms. So what rule is it called? It's the multiplication rule, I guess. The second one will be, I'm also forgetting the negative sign here, I guess. The second one will be sigma e to the negative sigma t, which is the derivative of this multiplying cosine omega dt sigma by omega d sine omega dt. Sign errors are highly likely here, so fortunately the notes should be correct. Okay, so everything has e to the negative sigma t as a factor, so we should look out for cancellations, and I know some happen, except that okay, all I know is that the cosines should cancel. If they are not canceling, then something is wrong. How do you see that? Oh yeah, okay, that was easy. Okay, all right. Oh, wait, save.
I love my colors. Don't pick up my colors. Okay, so cosines are gone, right?
So, okay, essentially what remains is sine omega dt times stuff, right?
So stuff times sine omega dt. The question is, when is that equal to 0?
For what t? Well, when does sine become equal to 0? When its argument is 0 or pi or 2 pi and all that stuff, right?
So when t is an integer n times pi over omega d, then this is going to be 0.
Do you agree with this? Yeah?
Okay, so integer multiples of pi by omega d. Let's go back, see the actual step response. So those values that I just talked about,
integer values, I said, that includes 0.
So this is the first time that the derivative is 0. We're not interested in that, right? That would be the case where n is equal to 0. This is the first non-zero time that we have. So therefore, this Tp is pi over
omega d.
All right? And the next time would be this, which is twice Tp. And this is 3 times and so on. But again, what we're interested in is this one. Okay? And there you go. We already have a solution for the peak time. It is pi by omega d. It's as simple as that. It's resisting. Okay. So that's that. So how do I find the peak overshoot? I have to substitute t equals Tp, the peak time, and see how much above 1 that is. And that's the overshoot. Right? So if I take pi over omega d, substitute it in this boxed expression for y of t at the end, okay, clearly sine will drop out because t is the time when sine is 0, right? So what remains is cosine. And so cosine pi is equal to what? -1. So, but then we have a factor of e to the negative sigma t. That's how we get this expression here. Oh, terrible way to mark it. Okay, so it is going to be this expression. And Tp, we already found what it is, so I can take this expression, substitute here, and I'm going to get this value for y at Tp. And to see what the overshoot is, I need to subtract 1 from this. So this is the amount of overshoot. This is how much above 1 I end up going. Okay? So clearly it depends on sigma omega d, but sigma and omega d themselves come from omega n and zeta. So I can eliminate sigma and omega d by substituting their values. And this is the final expression here in the box. That is the peak overshoot. An interesting observation about the peak overshoot, it depends. We have 2 important parameters characterizing our system, omega n and zeta, right? Peak overshoot doesn't depend on omega n. Couldn't care less. It only depends on damping, zeta. Okay? So why is that important? Well, that's important because it tells us the relative roles of omega n and zeta. Omega n is just a time constant, essentially. If you look at this plot, actually, let me go to the old one. That is cleaner. I messed this up. I marked too many things on this. Lecture 16. This is a cleaner one. Okay? So this is the step response. As you can see, this is actually, the time axis is not just time, it's time by omega n. And this tells you what the role of omega n is. If I change omega n, only the time scale changes. Things become faster or slower. The relative shape of the step response is unchanged. Do you see that? If omega n is 10 times as big, then this is compressed by 10 times, right? And the amount of overshoot or how, the oscillations and all that stuff, those features depend only on the damping ratio. Okay?
That's why we parameterize second-order systems with complex conjugate poles in this funny way. Instead of just the coefficients of the polynomials, we use this factorization with this parameterization so that we have two parameters, zeta and omega n, whose roles are very clear in shaping the step response. Omega n is a time constant. It compresses or stretches depending on what it is. Large omega n means you're farther away from the origin, the poles are. That means faster response. So it just compresses the step response, right? Zeta, on the other hand, defines the shape of the step response. Do we have overshoot? How much overshoot do I have? Those questions are answered by the damping ratio. And that's clear whenever we look at, oops, I'm actually still here. That's clear when we look at these expressions that we derived. Anything that has to do with time, and what are the parameters that depend on time? Rise time, peak time, settling time. In all of those, you should see a factor of omega n, right? Those are, all of them should depend on omega n, because omega n just stretches or compresses the step response, right? And indeed, if you look at TP, you have omega d in the response, and of course omega d depends on omega n, right? If you look at the things that I didn't talk about yet, the settling time and rise time, they either have omega n directly in the denominator, or they have like sigma, but sigma is omega n times the cosine of t, right? Theta. So omega n is always in the denominator, because that makes the role of omega n clear. Zeta determines the shape. As you can see in the peak overshoot, it depends only on zeta. All right, so for rise time and settling time, we only have approximate expressions. For the settling time, we do something very simple. We say, well, this looks like 1 plus an envelope, right? This envelope that goes to 0, right? So to find the settling time, we look for a time at which this envelope actually becomes 0.01, if it's 1% criterion for defining the settling time, right? So why is this an approximation? Because the actual step response is still wiggling within those bounds. So the time when the envelope is 0.1 is likely larger than the actual time when you're really 0.1, but we don't care too much about it because it's going to be close, all right? So that's why it's an approximation. So we set the envelope to 0.01, and the envelope, remember, is given by this. And taking logarithms of both sides and all that stuff, you get this expression for TS, right? Settling time is this. And the rise time, that's a rougher approximation. So when you look at these plots, you see that the actual rise time does not depend that much on zeta. It changes a little bit with zeta, but not a whole lot. So we take an average value of zeta 0.5 and see what rise time is at that value of zeta, and we apply that to all other zetas as an approximation, right? Okay, so with these formulas, now we have the key features of the step response related back to omega n and zeta, right? Do you now understand why we care about omega and zeta that much? You understand why this is a useful parameterization? All right. Cool. All right, so in particular, I'm just going to say these in words and keep going. So if you just take your omega n, multiply it by a constant, I said this only has the effect of compressing the step response, and this is basically a proof showing you why that's true, although you probably don't need the proof to see the plots for yourselves. So this is good to look at. So the summary. If I want a faster response in general, I need to select my omega n, which is the distance of the complex conjugate poles from the origin, to be larger. So this is an important thing you should remember. If the poles are far away into the left half plane, they are far away from the origin, that means you get a faster response. Okay? The distance from the origin essentially is a time factor. Yes. That means compressed. Or whatever the response is for that matter. I mean, if I give you poles, like it doesn't have to be 2 poles, any pole zero configuration, right? And then you have a certain response for that, right? And I take every pole and every zero, multiply all of them by 10. What happens to your response? It's compressed by a factor of 10. Okay? So your distance to the origin, the pole zero distance to the origin, is an indicator of time, like how quickly things are happening. Okay? So imagine like a balloon, and the poles are on the balloon. You're blowing into the balloon. It's becoming bigger. What's happening to the response is getting more compressed. Okay? So that's omega n. The effect of zeta is overshoot. Larger zeta is well damped, doesn't give you much overshoot. Smaller zeta is going to give you overshoot. Is there ever a value for which you have 0 overshoot? Let's look back at this solution. Peak overshoot, here it is. When do I get 0? Exactly 0 overshoot. So the overshoot e to the something, when does that become exactly equal to 0? If its argument is zeta equal to 1, because then you have e to the negative infinity, which is 0, right? So only in the limit when zeta is going to 1, that is when the poles are actually becoming real, you're getting 0 overshoot, right? So essentially, you always have a little bit of overshoot the moment you have complex conjugate poles. It may be small, it may be large, depending on the amount of damping. The overshoot in the frequency response, which we call resonance, is a different story. There we have some resilience until zeta becomes something like 0.7. If you're reducing from fully damped 1 to 0.7, we still have a flat, monotonically decreasing frequency response. Only when zeta goes below 1 over square root of 2, which is roughly 0.7, we start getting these overshoots. So the overshoot situation is different between the step response and the frequency response, right? Okay. So now, how useful are these formulas? Because they're only for second-order systems, right? Well, it turns out they're actually still quite useful. So what people do in practice is, if you have a system with a bunch of poles, right? You may have 2 that are sort of closer to the imaginary axis, and many others far away. In those situations, you can approximate your transfer function with a second-order one that captures those 2 poles. What happens to the rest? They are still there, but remember the effect of poles that are far, far away. They settle down very quickly, right? Because they are far away. The farther away you are from the pole, just imagine looking at this expression and doing a partial fraction expansion, right? These far away guys will have their own a over s plus alpha types of things, but alpha is really, really negative. So you're going to get e to the negative alpha t that will immediately die off, right? So therefore, we don't worry too much about those. Those are fast stuff. And by the time I look at the slow response, they disappear already, right? Again, if I'm interested in the response to a pilot's command, just give me a second. There are so many dynamics under that, right? There are aerodynamic coefficients. There's the, what do you call these things? Hydraulics that turn on the flaps, whatever you're tuning, right? So all of these things have their own dynamics. So if you want a very accurate, detailed model of this transfer function from the pilot's command to the actual elevation, you'll have many, many poles, right? But most likely, many of them are happening, they represent physics that's happening at a fast time scale. Things that settle down very quickly. Okay? And those would be translating to poles that are far away, and it's okay to sort of ignore those with the premise, the assumption that they'll settle down very quickly. So then you capture the slowest things. Those would be the poles that are closer to the origin. Yes, you had a question? Well, but then it won't be a transfer function with real coefficients. Because essentially you're looking for roots of a polynomial with real coefficients. If you have a complex one, and if it's not accompanied by a conjugate, then the polynomial has to have complex coefficients, which in our physical examples they don't. Right? Other questions? Shall we take a break for a few minutes? All right, go take your break.
Okay, so we'll now talk about a variant of the Laplace transform that's called the unilateral Laplace transform. Not much new here, really. We'll just do a little tweak on the Laplace transform. So the traditional definition was integral from where to where? Minus infinity to infinity, x of t e to the negative s t dt, right? The unilateral, so this is the regular Laplace transform. Unilateral starts integrating at 0. That's the only difference. Obviously, we need a different notation so we don't mix them up. So I'm going to use this curly x. Hopefully, it will be distinct from the other one. So now I start at 0, go to infinity, x of t e to the negative s t dt. Big deal, right? We just change the limits of the integration. What is usually done is, in case that x contains impulses and stuff like that at 0, you will want to include them, so you put a 0 minus, meaning that, start integrating just before 0. So don't miss, if there's a singularity at 0, don't miss that. That's the point of that. But in most applications we see, that will not be an issue. There will be no difference between 0 minus and 0. Okay? So with this, if I ask you the Laplace transform of delta, the delta function, the unilateral Laplace transform, you would say it's 1. If I did not do the exception for 0 minus, you wouldn't know how to answer this question, right? Okay. So, little example. So let's say we have x of t e to the negative a t u of t. What's the Laplace transform? 1 over s plus a. What's the Laplace? What is the unilateral Laplace transform? Same, because it's already a right-sided signal. Start at 0. For any signal that starts at 0, obviously there's no difference, right? Now let me take this signal. This is this signal, right? So let me shift it to the left by 1. So now I'm going to look at this, right? So x of t, so that's my example 2, is e to the negative a. What do I need to do to t to make the whole figure shift to the left by 1? T minus 1 or t plus 1? Plus 1. U of t plus 1, right? T plus 1. Okay, so now what is the Laplace transform of this, the regular Laplace transform? Time shift rule, right? If I shift something to the left by 1, then I'm multiplying the Laplace transform by e to the negative s. No, e to the positive s, sorry, because I shift to the left. If I'm moving by t0 to the right, then it's going to be e to the negative st0 x of s, right? So therefore now t0 is negative 1, so I get a positive s times 1 over s plus a, right? Now clearly the one side of the Laplace transform will be different, right? Because after time equal to 0, so what is the value of this at time equal to 0? E to the negative, at time equal to 0, I said, no. E to the negative a, right? So really, x of t then is e to the negative a times e to the negative at ut for t greater than or equal to 0, because you're looking at this part, right? Right? So it still decays with the same rate, but it started not at 1, but e to the negative a. So the one side of the Laplace transform, therefore, is the Laplace transform of this guy, which is already right-sided. Okay? So the unilateral Laplace transform will be e to the negative a, which is accounting for this, times the Laplace transform of this, because that's already right-sided, so it's the same. So 1 over s plus a. So that example tells you that for signals that have stuff happening before time equal to 0, the unilateral and the regular Laplace transforms, or I guess regular is not a good term. You would say bilateral, I guess, are different in general. All right. A lot of the properties of Laplace transforms we discussed actually hold as is in that case. All you have to do, I'm not going to do that for you, but all you have to do is go look at the properties, look at their proofs, ask yourself if it really depended on where we started integrating, right? There are a couple of differences. There is the one case where an important property goes out the window when we do unilateral Laplace transforms, and that is convolution. Because convolution, you flip, drag, all that stuff, you can't just truncate at 0, right? So there is a supposed convolution property of unilateral Laplace transforms, which really says nothing. I mean, it basically says there is no convolution property for unilateral. But let me write down what it says. It's from the book. Okay? So x1 star x2 of t gives us a one-sided curly x of s equals x1 of s, x2 of s, if, that's the important part, x1 of t 0, t negative, x2 of t 0, t negative. Of course, then you're talking about the regular Laplace transform. Of course, that property is there, right? So really, that's a non-property in the unilateral case, right? So don't even take it seriously. Another property that's actually useful, and that's tailored to the unilateral case, is the differentiation property. And I'm not going to talk about any other properties, because the reason I'm even doing the unilateral, the one-sided Laplace transform, is because of this property, which has a very important use, as we will see. So if I, reviewing what we had for bilateral case, if I had x of t giving me x of s, what did dx dt give me? Come on, you gotta remember this. There's no j omega. We're doing Laplace transform. S. S x s, right? Derivative means multiply with s. That's Mr. Heaviside, right? He said, you know, who cares about derivative integral? There are just multiplications with some s. He actually called them p, in fairness, but that's just a complex variable. All right, so that's what we already knew. So this is the bilateral case. Let's now talk about the relevant property for the unilateral. So if x of t has unilateral Laplace transform curly x of s, then d by dt x of t has unilateral Laplace transform s times x of s, but then there's a provision for the initial value, minus x of 0 minus. All right? So that is the unilateral property, unilateral differentiation property. The only difference, obviously, is this guy here. All right, why is that true? That's very straightforward. So what we are doing when we are taking the unilateral Laplace transform of this is we are integrating from 0 to infinity dx dt times e to the negative st dt. Right? I guess this is something you would call integration by parts, although I never do it. I never apply the formula for integration by parts. I try to see this as the derivative of something big minus something else, right? So this looks to me like the thing in parentheses here looks like d by dt of x e to the negative st, except that the derivative of this would give not only that, but it would give me negative s times x e to the negative st. So if I add that, then I have this term here, x of t e to the negative st, okay? So what's in brackets here is the same thing that was in brackets here, okay? The two are the same if I didn't mess up the signs, all right? So that means then I'm doing this integration. But the first part of the integration is straightforward because dt's cancel. So I really have x of t e to the negative st evaluated at infinity and 0 minus. And then the second part is s times the integral x of t e to the negative st dt. Now, I already know what that is here. That is the one-sided Laplace transform, right? And it's multiplied by s, so that's where this term is coming from. And what is that? If s is in the region of convergence, that means x of t times e to the negative st is integrable. And to be integrable in the first place, you need to be exponentially decaying. So, therefore, at infinity, that's 0. At time 0, it is x of 0 minus. And that's where this comes from. All right? So the only difference from the bilateral case is we have to make an adjustment for the initial time. That's all. Otherwise, it's still multiplication by s. The reason we are interested in one-sided Laplace transforms actually lies in this property. This property and unilateral Laplace transforms allow us to solve constant coefficient differential equations. All right? Which the usual Laplace transform does not. Because when we're solving constant coefficient differential equations, we will be given initial conditions. And this transform allows us to take them into account. Where did we use Laplace transforms? They were critical for transfer functions of LTI systems, right? But for a system defined by differential equations to be LTI in the first place, there's a critical condition, remember? It has to be initially at rest. Okay, so that means when we are dealing with transfer functions, there is no provision for initial conditions. So we can't use transfer function reasoning to see what the solution is when there are initial conditions, right? If you are actually solving differential equations with initial conditions, unilateral Laplace transform is your tool, not the bilateral. And we'll see an example. But before, let's generalize this property just by induction, really. So if x of t gave me a unilateral Laplace transform curly x of s, then I just argued that dx dt of t will give us s times x of s minus x 0 minus. This is the little x, by the way, the value of the signal. Okay? What can we say about the second derivative? Well, we have to apply the same rule twice, right? Because that's really d by dt of dx dt. I already know the unilateral Laplace transform of dx dt in the line above, so I have to apply the same rule again. So accounting for the outer derivative now, accounting for this, we have s times the unilateral Laplace, I'm inventing some notation for it now, of dx dt minus what? Remember, I'm just applying the rule for this now, right? So it's going to be s times the Laplace of what's inside minus the value of the signal at time 0. But what signal am I talking about? dx dt, right? So it's going to be dx dt at time 0. Okay? And that I already have. It's here. So this is s, x of s minus x 0 minus. All right? So multiplying this by s, I'm going to get s squared x of s minus s times the value of the signal at time 0 and the value of the derivative of the signal at time 0. Right? So that's the rule for the second derivative. It really is not a new rule. It's a repeated application of the same rule. So I'm not going to write it for higher derivatives. If I wanted to, it would probably look like this. The nth derivative would have, in the unilateral Laplace, s to the n, right? X of s to the n minus 1, x0 minus, and you can predict the rest. There's a pattern here, right? Okay, that's all we need. So this property alone is enough to solve differential equations with constant coefficients if I give you enough initial conditions. Now, sometime in your life before coming to this course, I'm sure you studied these differential equations. How many people have never ever seen a constant coefficient differential equation? How many of you have never ever solved one? Okay, if you took 16b, you're probably unsure whether you solved one really or you didn't. But let's be optimistic and let's say you solved one. But you may have come here having taken not just 16b or not 16b, but some more traditional course that solves constant coefficient differential equations in a traditional way. First, proposing a particular solution and the homogeneous solution and adding them up. So you're not responsible for that method in this course, but I'm going to give you an example and remind you of doing it that way, and then go to the alternative which you are responsible for using the unilateral Laplace transform. And here's my example. The example is we have a second order differential equation, dt squared plus 3 times dy dt plus 2 y of t equals e to the t. And we are solving this for time greater than or equal to 0. To be able to solve it, you would need to be given initial conditions. So in this example, there's nothing impulsive at the input at time equal to 0, so I'm not going to have to deal with these 0 minus things, right? So it's just the solution is continuous after all. So let's say we are given 2 initial conditions. To solve a second order differential equation, you need 2 initial conditions. To solve an nth order differential equation, you need n initial conditions. So you would need to be given dy dt at 0 as well. These two would need to be specified. I'm not going to make up arbitrary numbers. Let's just leave those as givens, symbolically, a and b, okay? And we'll find a solution that depends, obviously, on those initial conditions, a and b. But we'll keep it general, so we're not going to specify a and b, okay? So, traditional way in math 50-something. Do they do it in math 50-something? 54, okay. So they probably tell you to first think of a particular solution, yp of t. Something that somehow when you substitute it in here, it satisfies the equation, okay? So, and then they probably teach you that, you know, it should look kind of like the forcing function, which is e to the t in this case. So you can trust that they are telling you the truth and, you know, postulate some number, yes? Yeah, I'm just talking about the particular for now. There is also a homogeneous. Let's start with particular, something that somehow works, okay? And if I postulate something like b times e to the t, then I stick it back into the equation, right? What is the second derivative of this? I guess e to the t was a little boring because there's no power. If it was e to the 2t, then the derivative would bring a factor of 2, right? But now I don't have that, so everything is going to look like, so this is going to look like b times e to the t This is also going to be b times e to the t, and this is going to be b times e to the t, right? Anyway, I have 6 of those, right? So that means 6 times b times e to the t is e to the t, and there you go. You have a solution for b. Should be 1 over 6. Okay? So that gives you a particular solution. And then we solve for what's called the homogeneous solution. That means, what if there was no forcing? If the right-hand side was just 0. So d square y dt square plus 3 dy dt plus 2y equal to 0, right? What are the solutions for this? The way to do this is to write the so-called characteristic polynomial, lambda square, because lambda is a complex number, lambda square because this is the second derivative. This lambda is really just like our s, and you'll see that in a second. 3 lambda for the first derivative plus 2 equal to 0. You solve for the roots. Lambda 1 will be negative 1. Lambda 2 will be negative 2. So then the homogeneous solution, y(h) of t, is any linear combination of these guys. Some a1 times e to the lambda 1t and a2 e to the lambda 2t. The point is, if you look at either root of these, for any lambda that's the root of this characteristic polynomial, e to the lambda t solves this differential equation. And any coefficient times e to the lambda t still solves the differential equation. Okay? If I pick 2 independent lambdas and make a linear combination, that still solves the differential equation. That's why we call this the homogeneous solution, right? So then we write a solution of this form. The particular one, which we found to be 1 over 6 e to the t plus a1 e to the lambda 1. Lambda 1 was negative 1, so I'll just write negative t plus a2 e to the negative 2t. Now, if you substitute this guy back into the differential equation, the original one with the forcing, it will still satisfy it no matter what a1 and a2 are, right? Because these two will make the left-hand side with the derivatives and stuff equal to 0, right? And this one will make the left-hand side equal to the forcing term. So the whole thing is a solution. So this is a slew. There's a continuum of solutions. For any a1 and a2, this is a solution. How do I select a1 and a2? By setting the initial conditions. So y0 was a. That means 1 over 6 plus a1 plus a2 is little a. That was a given. It was a parameter of the problem. Y prime of t is, again, 1/6 e to the t, negative a1 e to the negative t, negative 2a2 e to the negative 2t. So if I look at the initial condition for y prime, which is dy dt, of course, I have 1 over 6, negative a1, negative 2a2 equal to little b. So I'm essentially solving two equations in two unknowns. A and b are given. The little a, little b are given. We want to keep things symbolic, so we are not putting specific numbers there. What we are looking for is capital A1 and capital A2. And if you do your math, you get A1 equals negative 1/2. You can check this later, but it should be correct. 2a plus b. And A2 is 1/3 minus a minus b. All right? Of course, I could have given you initial conditions like 0 and 1, and these would come out to be specific numbers, but we are doing more generally. So that means the solution using the traditional method is 1/6 e to the t plus negative 1/2 plus 2a plus b e to the negative t and a2 times e to the negative 2t. That's the answer. All right, so that's pretty effective. So, but I don't expect you to do things this way in this course. I instead expect you to be able to use the unilateral Laplace transform. So how do we do that? Let's go back to our differential equation. Now we're not going to mess with any particular homogeneous. They'll come out naturally. Okay? 3 dy dt plus y, no, 2y equals e to the t. T greater than or equal to 0. Okay? So let's apply the unilateral Laplace transform to both sides. What is the unilateral Laplace transform of d square y dt square? We discussed that. It's s square y. I don't know how to make it curly y. So I'm just going to make up some strange shape. Y of s. S times y0, right? And that was a, the initial condition. And then minus derivative at time 0, that's b, right? Is that correct? All right. Plus 3 times dy dt. And this is s, y of s, minus initial condition of y itself, which is a, right? Plus 2 times y of s. So we are finished with the unilateral Laplace transforms of the left-hand side. Now I need the unilateral Laplace transform of the right-hand side, which is going to be the same as Laplace transform for t positive, e of t times u of t, right? And that is what? 1 over s minus 1. Okay? All right, the rest is solving for y of s. I have s squared plus 3s plus 2 y of s equals 1 over s minus 1. And then I have to take care of the ab terms. So I will have as plus b plus 3a going to the right-hand side. Do you agree? These are all the terms that were hiding here. This one and this one. And I carried them over to the right-hand side. Do you agree with what I did? Yes? No? Okay. So that means we are coming close. Okay. So, okay, so that needs a little bit more simplification. Okay, so the right-hand side you can write in this form, s minus 1. So essentially you keep this one, multiply these guys by s minus 1, okay? And when the dust settles, this is what you end up with. b plus 2a s plus 1 minus b minus 3a, okay? By s minus 1. This is the right-hand side simplified. I want to leave y of s alone. That means moving this term here into the denominator of the right-hand side. So I'm going to get this. Plus 3s plus 2. All right? Now, this term here, the one that I just highlighted, there's an eerie resemblance to the characteristic polynomial we were discussing here, right? This s lambda is now s, right? So, and we also know its factorization from here. We know the poles. So that means the whole thing here has 3 poles at -1, at -2, and at 1, right? So if I do a partial fraction expansion, that is going to look like a1 over s plus 1, so that since this is s plus 1 times s plus 2, right? And then a2 by s plus 2, and then another number b, not coincidence that I'm calling it b because that will actually correspond to the particular solution, s minus 1, okay? So the solution is going to look like this. Now if you go backwards and do the inverse Laplace transform, what is that? a1 e to the negative t plus a2 e to the negative 2t plus b times
e to the t, right? Okay, and that really is no different than what we proposed here, right? So we had the B, so this was the particular solution. This is our B. This is our A1, and this is our A2. Okay? When you do the, I didn't do this, of course, but you have to find your A1, A2, and B, right? So how do I do that? I write this whole thing into one giant expression, match the numerator of that to this. You get three equations in three unknowns. The unknowns are A1, A2, and B. You solve for them, and trust me, you're going to get this as your B. You're going to get this as your B. You're going to get this as your A1, and this as your A2. Okay? So the two methods are really equivalent. They give you the same answer. In fact, the steps are very much aligned with each other, right? I mean, finding the characteristic polynomial is like factoring out this term here into its roots, writing it as a product of S1 plus 1, S1 plus 2. The partial fraction expansion gives you terms that corresponds to the particular and homogeneous solutions, right? So are you convinced now that the unilateral transform is useful for differential equations with initial conditions? Yes? Good. Question? Well, when I said three equations, three unknowns, so you see in the numerator you have you have a second order polynomial, as squared plus blah, 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 right? That has three coefficients. You know those. So little a and little b are initial conditions. They are given, right? So really you have the second order polynomial and you know what the coefficients are. So then you have to equate, well, you see, but maybe others don't. What's happening? So you have to make sure this expression here matches this expression. Okay? So this needs to be simplified, so you're going to have something like A1 S plus 2 S minus 1 plus A2 S plus 1 S minus 1 plus B S plus 1 S plus 2 divided by S plus 1 S minus 1, blah, 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 right? So denominators match. That's not the issue. The issue is to match this numerator to this numerator, and that will give you three equations for A1, A2, and A3. All right? Got it? Okay. So that's the idea, and I'm not going to make a big deal of this. It's a great tool for solving differential equations. That way you don't have to go back and remember the 54 stuff. What was the particular solution? How do I do it? So everything follows from the inverse Laplace transform. Okay, so now a lot of you were unsure when you said you took 16b. Did you really learn how to solve these differential equations? So let me just briefly walk you through. One of my purposes in this course is also connect the dots, right? So we teach you somehow what we think in our minds is the enlightened way of solving differential equations. What? That's not from me, is it? Okay. All right, so let's do a little flashback. I can see you trembling and sweating already. Okay, so how would 16b do it? Or how would 16b tell you to do it and not do it? Or, okay, so second derivative, pt squared plus 3. And if you're getting PTSD from this, you can leave. I don't blame you. 2y equals e to the t, right? All right. In the jargon of 16b, this would be the input. In this course, we I think in 16, I don't know what notation they've been using the past couple of years when I wasn't teaching it, but x used to be state, u used to be input, I think. But to be consistent with our notation in 120, x is the input, okay? So that will be our x of t. So we would like to put this in a state space form, all right? So I would like to write somehow two. So since this is a second order differential equation, I would need two states, right? So one way to do that is to define your first state z1 to be y itself. And this is a method that will never fail, okay? So, and you can choose z2 to be dy dt. With those two, the first state equation is automatic. It just comes from these two definitions, z1 dot, or d, let me not use d dot. Dot means d by dt, but I don't want to create unnecessary notation. D by dt of z1 is z2 by definition. I don't even need to look at the original differential equation in blue to say that, right? It follows from my definition of z1 and z2. The differential equation itself will come into play in writing the second state equation, d by dt of z2, because that is y double dot, the second derivative of y, right? d squared y dt squared, correct? And now using this equation, that is minus 2y minus 3 dy dt plus x of t. Agree? And going back to our state notation, that is just, this is z1, z2, right? 2z1 minus 3z2 plus x, all right? And y of t is z1 of t. Okay, anyway, we don't really have to worry about y of t here. It's clear it's z1 of t, but anyway. So what is the, so I can write this as dy dt of a vector z that consists of z1, z2 equal to a times that same z plus a matrix B or column vector B times x of t. All right, what is A, what is B? Zero, 1, minus 2, minus 3, they came from these two, right? And then B, there was no input in this equation, no input, right? So the first entry is 0. The input appears in the second equation with coefficient 1, so a 1 comes here, right? So A and B are equal to this. Okay? So you have your state equation. So what do you do with it? What 16 probably told you to do is to diagonalize A. Okay? So you essentially need to find eigenvectors v1 and v2, stack them side by side, and that's of course v1, v2 times the diagonal lambda 1, lambda 2. Okay? Really, what this equation says is A times v1 is lambda 1, v1, the first eigenvalue, eigenvector pair. A times v2 is lambda 2 times v2, right? So therefore, so this is a 2 by 2 matrix, right? 2 by 2. So that means eigenvectors put together side by side, inverted A times, again, the same matrix, is going to give you the diagonalization. Okay? So that's the first step. The second step is to define a new state that is actually in the diagonalized form. So let's call that z tilde, inverse z. So when you do that, z tilde dot is going to, or I said I'm not doing dots, right? So d by dt of that is going to be the diagonal matrix lambda 1, lambda 2
z tilde plus that inverse times 0, 1 times x. Okay? What's the point of this diagonalization? That breaks down this vector differential equation into first-order differential equations. So you're going to have d by dt z1 tilde of t equals lambda 1 z1 tilde of t plus something times x of t, and d by dt z2 tilde of t is lambda 2 times z2 tilde of t. The nice thing here is that these differential equations are completely independent of each other. So you're really solving first-order differential equations. Okay? Whether you liked it or not, in 16b, the philosophy was, know how to solve a first-order differential equation, very simple structure of the solution. And any higher-order differential equation can be broken down into first-order ones through diagonalization. And then you apply the formula for a first-order equation, and you can reassemble the solution to the actual thing. Is that very practical for actually solving by hand the differential equation? Debatable. But the goal isn't, to be fair, who in this day and age really solves differential equations by paper and pencil, right? So this was showing you, when you do things numerically, this is how it's done, okay? So that's why we do it that way, whereas 54 and other classes assume that the goal is to do this by hand, okay? So as you can see, to do it by hand, this is not the best method, and that's why I'm not finishing it. But it's good to see that this lambda 1, remember the eigenvalues and the poles match up? So the poles we saw were -1 and -2, right? So the solution to that will include an e to the negative t term plus some terms that depend on the input. And the solution to that includes e to the negative 2t. Okay, of course, the initial conditions will affect these two, right? But the important part is that you get these terms because -1 and -2 are eigenvalues. And that's why they actually show up in the actual solution. Okay? So this was just to connect with 16b. You're not going to do it in this way in this course. Neither are you going to do homogeneous particular. If I ever ask you, in fact, in the upcoming homework, I think I do. If I ask you to solve a differential equation, you just do the one-sided Laplace transform. Okay? And it's a good way to practice Laplace transforms, if nothing else. All right. So do you have any questions for me? I don't have enough time to start a new thing all over, so I'm going to stop here. But I'll also remain here to answer any questions. This will be giving you back the extra minutes I've been stealing through the semester at the end of the course. I give you 5 minutes back. And I'm sure I'll take it back in the future too. Okay, see you guys next Tuesday.